Hi everyone. Welcome to the optimization class. Today, we are going to talk about the phenol production using optimization method and tools. Before we start, let us introduce the 5 main contributors of the day. They are Toong Fung, Sai YUAN, Yan, and SHIKI. There are a total of 5 chapters for this optimization assignment of phenol manufacture. Each will be conducted and explained to achieve the objectives of this assignment. Hi, my name is SHIKI. In Chapter 1, Sustainability and Feasibility of the Phenol Production Projects will be studied. Basically, phenols are a class of chemical compounds consisting of hydroxyl group, OH, bonded directly to an aromatic hydrocarbon group, while its feasibility will be elaborated based on 3 parts: technical, economic and environmental. So why phenol? The reason we choose to produce phenol is because phenol has become one of the most traded chemicals in 21st century due to its high application and high consumption. It can be produced by an intermediate raw material of cumene to produce desired phenol and byproducts of acetone. Following the chain of production, phenol and byproducts acetone can produce a series of different chemicals for good profitability. Besides, it is expected to continue growing 5% per year in Asia. This figure shows the global market of phenolic resin, one of the major products formed by using phenol, by geography in 2016. In technical feasibility, the idea of retrofitting is utilized in the plant. Existing energy and mass balance is improved with the aid of separation train synthesis, recycle stream and intensive heat and energy network. For economic feasibility, phenol is expected to increase its market demand, especially in polycarbonate sector. One of the product formed by phenol, BPA, is expected to grow an extra of 6.8% from 2017 to 2022, while its segment is estimated to grow to a value of US $8.5 billion at 2022. The production of phenol using cumene as raw material via oxidation are encouraged due to the inexpensive raw material and relative high yield and efficiency. Hence, it is profitable and feasible economically. In terms of environmental, 3 major pollutants are emitted to atmosphere, which are acetone, acidified wash water and acetophenone. Proper engineering controls have been proposed to secure the safety of the process and operation. For instance, wastewater treatment, reverse osmosis and neutralization treatment. Furthermore, acetone byproduct has some dangerous properties such as colorless, highly flammable and corrosive. With the installation of engineering control and proper planning for environmental safe process, it is environmental feasible to produce phenol chemical.
Hi, my name is YUAN. Now I will discuss Chapter 2, which is the base case development of phenol. In phenol production, there are 4 alternative routes can be used, with each having its own pros and cons. The selection of phenol production method is based on feasibility, economy and sustainability. The first method is oxidation of cumene. Cumene can be produced commercially via alkylation of benzene with propylene over an acid catalyst. In cumene oxidation, cumene is added to oxygen to form cumene hydroperoxide. After that, cumene hydroperoxide is mixed with dilute sulfuric acid and is decomposed into phenol and acetone. In this reaction, phenol is the favorable product and acetone is the byproduct. However, acetone can be sold or handled by other unit operations to form useful acetone derivatives for a better profit. The second method is toluene 2-step oxidation. Toluene is used as feedstock for toluene 2-step oxidation. It is first oxidized with air in reactor to form pure molten benzoic acid. After that, benzoic acid will be transferred to second oxidizing reactor where it is oxidized to phenol when mixing with air and steam. This reaction is exothermic and external cooling is required to maintain the process condition. In addition, multiple distillation columns is required for separation process. The Raski cooker process. This method involves the intermediate chlorobenzene. Firstly, Chlorobenzene is obtained by oxychlorination of benzene with hydrochloric acid air mixture. After that, chlorobenzene will undergo hydrolysis process to generate phenol. This method has an overall selectivity of 70 to 85% for both oxychlorination and hydrolysis processes. However, it limits the benzene conversion of 10 to 15% to control the evolution of heat at the fixed bed catalyst and to suppress the formation of dichlorobenzene. Besides, the catalyst must be regenerated frequently due to carbon deposition, and the involvement of hydrochloric acid requires corrosion-resistant equipment in the plant. Sulfonation of benzene is the oldest method for phenol manufacture. It includes 4 major chemical reactions of sulfonation, neutralization, fusion and acidification. This technology is seldom used in the current phenol manufacturing industry as the production rate is slow and it requires several purification processes. From all the alternative pathways stated above, the phenol production through oxidation of QING is selected by comparing the advantages and disadvantages of all the processes and the cost of raw materials. QING oxidation process has high operation stability and efficiency due to highly developed and proven technology involved. Even though the cost of raw material is comparatively expensive, it is highly feasible and profitable due to the contribution of high product conversion and production of useful acetone byproduct.
Hi, my name is Timothy Takey HOCK and I will be presenting on how the separation train sequences are selected. Based on the base case of design, the relative volatility of each component is calculated and shown in the table presented. The 4 components are labeled and arranged according to their relative volatility, which are acetone, A, QING, B, phenol, C, and carbinol, D. A separation sequence tree is generated on all the possible pathways that the components can be separated. There are 2 methods that were used to decide the optimum separation pathway. The first method presented here is the heuristic method. There are 6 heuristics that are considered here. The first heuristic states that corrosive substances are to be removed first. In the case of phenol production, the byproduct acetone should be removed first. The second heuristic is to remove products as distillates at every separation train, which points to the direct sequence. The third heuristics require the removal of substances of the higher molar percentage first. The fourth heuristic states that the order of separation is according to the relative volatility, where the most volatile substance is removed first. The fifth heuristic states that the product that requires the highest purity should be separated last. The last heuristic states that the top and bottom of the distillation columns should be in equimolar at each separation train. From the heuristics, it can be seen that the direct sequence is the best sequence that adheres to heuristics 1, 2, 4 and 5. The second method used to determine the optimum separation pathway is the quantitative method. By simulating each of the separation sequence, the vapor flow of the distillates for each column can be determined. By adding the vapor flow for all the columns, the minimum vapor flow of the separation sequence can be determined. As seen in the slide, the first sequence, which is the direct sequence, has the lowest minimum vapor flow and is the optimum separation sequence. As seen in RPFD, the direct sequence is used, with acetone removed first, followed by QING and lastly between phenol and carbinol. After finding the optimum separation sequence, parametric optimization can be done to improve the conversions of the plug flow reactors, which is discussed in the next section.
Hello, my name is Fung. For my part, I am going to explain Chapter 4 Chemical Process Optimization in details. In order to optimize the phenol production efficiently and to make the process become economically feasible, there are several types of optimization which can be used. For example, parametric optimization and topological optimization. Parametric optimization focus on adjusting process variables, such as temperature and pressure, thus, improve the objective function. In the case of topological optimization, focus on adjusting the layout of the flowsheet, so that the objective function can be improved. For our case, Parametric optimization was used to optimize the extent of the reaction for all of our reactors, and topological method was utilized in Chapter 5. In this phenol production process, parametric optimization was used, and there are many process variables which can be manipulated. The objective for this optimization is to maximize the revenue for this process. In order to do so, we have to maximize the conversion rate of the plug flow reactor, PFR 100, PFR 101, and PFR 102. Thus, phenol mass flow rate will be increased, and therefore, revenue can be maximized. Few of the parameters can be adjusted in order to meet the requirements above, such as temperature and pressure of fresh QING, temperature and pressure of fresh air going into PFR 100, Air 1, temperature and pressure of fresh air going into PFR 101, Air 2, and temperature and pressure of fresh air going into PFR 102, Air 3. Therefore, the parameters are adjusted accordingly in order to optimize the process. There are several constraints are made in the progress. The first one is the conversion of the combined reaction in PFR 100 must be more than 3.5, followed by the second PFR 101, conversion of QING reaction must be more than 3.0. Last but not least, the conversion of the QING reaction in PFR 102 must be more than 2.0. After the optimization process, the conversion for PFR 101 and PFR 102 decreased from 7.52% to 6.33% and 4.79% to 3.91% respectively. However, the conversion of PFR 101 has increased from 7.83% to 9.42%. Therefore, we can conclude that conversion rate in PFR 100 and PFR 103 has to be decreased in order to increase the conversion rate in PFR 102. Also, the mass flow rate of phenol has increased significantly from 165.0 kg/s to 199.6 kg/s. In overall, the revenue of this process has been drastically improved from $141.90 to $171.70.
Hi guys, my name is YUAN. Today I am going to talk about heat and energy integration. In our phenol production plant, distillation is a major energy consumer. As we can see, the condenser and reboiler in the distillation column require a large amount of energy to separate the products. In order to synthesize a heat exchanger network to increase efficiency of heat recovery, pinch point analysis is used. The first step will be forming of PTA table. The minimum temperature difference selected is 10 degrees Celsius to have better heat transfer coefficients for petrochemicals industry. In order to make the hot streams cooler and to make the cold streams hotter, new temperatures are calculated with addition and subtraction of minimum temperature difference divided by 2. Next, steam populations are drawn and the temperatures, heat capacities of each interval are calculated to determine the respective enthalpy changes. The enthalpy changes calculated are placed in the heat cascade table to identify the pinch point. Pinch point is identified when the enthalpy change is 0. In our case, we have 2 pinch points. As we can see, there are 2 pinch points. The below pinch will use the lower pinch hot and cold temperatures, whereas the above pinch will use the higher pinch hot and cold temperatures. We will first look at the below pinch region. According to the rules, the hot streams must have higher heat capacities than the cold streams. Only H4 and H5 fulfill this condition, and both the streams will be matched with C1 and C2. The proposed matches are H4C1 and H5C2. In above pinch region, there are 2 cold streams and 1 hot stream. The rules stated that in above pinch region, the cold streams must have higher heat capacities than the hot streams. As H6 is having lower temperature than C4, the hot stream cannot transfer heat to the cold stream, and thus, the proposed match will be H6C3. After connecting them with heat exchangers, these streams can be tipped off. Extra utilities are used to provide sufficient duties required. As we can see in the process flow diagram, There are 3 heat exchangers that replace the original heater, reboiler from first distillation column and condenser from third distillation column. The duties required for condenser of first distillation column, condenser and reboiler of second distillation column are reduced. This leads to an increase in heat efficiency and costs reduction. Now, I will conclude on what we have learned. In conclusion, the production of phenol is feasible and sustainable. There are 4 industrial methods to produce phenol, and the oxidation of QING process is chosen due to high operation stability, efficiency and production of valuable byproduct acetone. In the study of optimization, there are 2 types of optimization, which are parametric and topological optimizations. Both optimizations are showed in this case. The main objectives of optimization is to maximum heat recovery and minimize utilization of utilities. Pinch point analysis is used to synthesize a heat exchanger network to reduce costs associated with energy consumption. In this retrofit design, 3 heat exchangers are used to increase heat recovery and to reduce the duties and utilities required. Our class session has come to an end. Thank you guys for watching and hope you guys enjoy the video.